Here. The problem we were working on yesterday, we'll finish that tomorrow. So today I want to talk about something that's more related to the lab we're doing today. And that is, let's say I had a reaction that consisted of some reactant A reacting with some reactant B in this stoichiometric ratio to make products here. The products could be whatever.
I have a question. We all want to know, is the lab due today? Or is the laboratory due today? Okay, look, I came in late yesterday, so you can't really, blame me.
Yeah, I talked about this yesterday at the beginning of class. Yeah. When is the lab due? Thursday. Right. Nothing's due today, so you're okay.
All right, that's all.
Okay. So if we have a reaction like this, we can follow the speed of the reaction by just monitoring the concentration of one of the reactants here. So let's monitor the concentration of A and then see how A is being consumed over time. So let's say we collect some data here, and then half of A is consumed in this amount of time, and then another half is consumed, another half is consumed. And so it looks something like this. And so the question that is asked is, let me not ask it this way. Let's just do this. The order with respect to the concentration of A is, what does it look like to you?
First.
All right, we'll go with first. Is the order with respect to A first order? Okay, the order with respect to A is first order. We'll just leave that as a statement. And what would you say? A would be yes, B, no, and C, what would C be?
Not enough.
Not enough information. Say not enough info. And so looking at this, you probably can eyeball it. It's not linear for sure, right? And so I use first order, second order, or something like that. And so looking at this, how many people would agree the order with respect to A concentration is first order? Okay. What about B? No. How about C? Not enough info? All right, why do you guys say it's first order? Nobody picked B, so if you picked A, why would you say it's first order?
I thought it would be first order because you look at the T1 half.
Yes.
You see that the concentration increases by half every time you go, right?
Right, that's good. So we look at the T1 half, and it looks to be doubling, getting cut in half, maybe because my drawing's not so great, or about the same. Yeah, each increment is the same, roughly, which means that T1 half is constant, which tells us it should be first order. So that makes complete sense that this looks like a first order or exponential decay. But the answer is not A. The answer is C. And so why is that?
We have no data
The reason is because I didn't tell you something when we were talking about these curves yesterday. The thing that I didn't tell you is everything that we talked about, those curves, are for single reactant reaction. That is, A just goes to product. What happens when we have multiple reactants is this. Both reactants influence the rate of the reaction. And so as A is decreasing, normally at first order, A gets cut in half, the rate of the reaction gets cut in half. A gets cut again, and the rate of reaction gets cut again. And so here we'd have the initial rate of reaction. This would be 1/2 the initial rate of reaction, 1/4 the initial, 1/8 the initial rate of reaction as we're proceeding. But at the same time A is being consumed, what's happening with B? B is being consumed twice as fast. And so what influence does B have on the rate of the reaction? Because if B's concentration is falling off a cliff, then is that going to slow the reaction down as well? It could very well be. And so what we see here is this. When we have multiple reactants, we need to know the influence of both A and B. And so we must know dependence, the rate dependence on the concentration of B. And so that's the piece of information we're missing, because what we see is we can see the composite effect. We see this is the combined effect of both A and B. And what we call this is, we say the overall order of reaction. Overall order is first order. Okay, now what that means is this. It means it could be, first order in A and zero order in B. That is, B has no impact, right? That could very well be. And so this statement might be true. It could be first order in A if it were zero order in B. Or, let's say it's zero order in A. If it's zero order in A and first order in B, what should this graph look like? Let's say zero order in A, first order in B. It should look first order because it's the overall effect. And so we must know this. And basically, this is how we're going to visualize this. When we have multiple reactants like this, A plus 2B goes to product, then the rate of the reaction depends on both the concentrations. And so the rate law is going to look like this. It's going to have the rate constant times the concentration of A raised to some power m, and the concentration of B raised to some power n. Where m is the order with respect to A, n is the order with respect to B, and m plus n equals the overall order. And so if we have, as an example, let's say that m is 1 and n is 0, then it has no dependence on B. And the rate is just going to depend on the concentration of A. So as the concentration of A decreases, then it's fine. So this would be indeed first order in A. But if we have this example, m equals 1, not m equals 1, m equals 0, and n equals 1, then it's going to be zero order in A. And so if we plot it, it should look like this. What is zero order? Zero order is a straight line because as the concentration changes, it has no impact on the rate. The slope just stays constant. Right? And so we get a straight line. Whereas when we look at B, now B has a first order dependence. If B has a first order dependence, then we look at B, concentration versus time. What should this graph look like? Well, it should be just a regular first order exponential curve like this decay. Right? So now let me ask you stoichiometrically. You know, stoichiometrically, we need an A and two B's to react. So as B is reacting exponentially with A, are we going to consume A linearly? Is that even possible? In other words, do these two curves agree? No, it's impossible, because for every B that we consume, we're going to consume half a mole of A, let's say. And so basically the rate of consumption of A is going to be 1/2 the rate of consumption of B. And so if we're consuming B like this, then we must be consuming A not like this. It cannot be a straight line consumption. It has to be like this. A is being consumed at half the rate. It's got to be a curve, right? Does that make sense?
So with the initial we have of the original
No, well, the initial is whatever you want,
Oh, okay.
and then you're just going to consume it.
Okay.
And so if actually we'd start at the same initial, just consume it like that. Does that make sense? And so what we have here is, if we have multiple reactants, then what we see is the composite effect. We don't see the individual effect. So how do you determine the individual? How do you deconvolute this? How do we determine what M and N are for the reaction A plus 2B yields product? The problem is we can't do it off the graph of A alone, and we can't do it off the graph of B alone, because those are the overall, showing the overall order of reaction, right? They aren't showing the individual order. And so graphing A versus time, or B versus time, just gives us the overall order. There are two methods that we can use. Method one is the pseudo M order reaction. What is pseudo M order? Pseudo M order is doing this. When we do pseudo M order, we make the concentration of B so large that it changes negligibly over the course of reaction. And so one way of thinking about this is, to make water balloons, you'll need balloons and you'll need water, right? And if you have so much water, like let's say a swimming pool's worth of water, and just a few balloons, then is the amount of water really going to change over the course of the... No, just negligibly. And so what we do is we make B so big that at the start of the reaction we have a huge concentration. At the end of the reaction we have a huge concentration. And so this way we eliminate the impact that the change in concentration of B would have. And so the rate should depend on both A and B. But if B is so large, it's fairly constant over the course of the reaction, then B doesn't really change. And so the only thing changing is A. We're losing A, we're losing half of A, 3/4 of A, etc., etc. And so the A concentration is changing dramatically, B is not really changing. And so that's fairly constant. We take these two constants and put them together. Doing that, we form a new constant called K prime. So we'll take the rate constant times the concentration of B to the N, and we get K prime, concentration of A to the M. So now, when we plot the concentration of A versus time, we've just eliminated the influence of B, so all we're seeing is the influence of A. And therefore, we can just go ahead and compare the plots. A versus time. Is it linear? Is it curved? How does it decay? And based on this plot, we can determine the order. In other words, what's that?
The order of A only.
Oh, the order of A only. And so we just make a plot of A versus time and then see what kind of curve it is. But what about B? What about N? We still need to know how N impacts the rate. And so how can we do that? Yeah, we do the opposite, which is make A so big that the change is negligible. And therefore B is changing dramatically, and B will impact the rate. And so here, just make the concentration of A very large so that it's fairly constant over the course of the reaction and it doesn't really change. And then we make a plot of the concentration of B versus time, and then C. Is it linear? Is it curved? And what kind of curve is that? And then we can get the order. Once we have the order with respect to A and the order with respect to B, then we know how this behaves. And so let's give an example. Let's say we did this for a more complicated reaction. Let's say we had an A plus B plus 3C. This goes to product. And then let's say the rate law, we did this and we got that Ka, it's first order in A, first order in B, and first order in C. Now during a normal reaction, if I'm looking at A plus B plus 3C, let's say I cut A in half. And so I start off with A initial, and I cut it in half so I have 1/2 A initial. If it's first order in A and I cut the concentration in half, what happens to the rate? The rate gets cut in half. And so I expect the rate to get cut in half. Let's say B, I start off with B initial, and then I'll cut it in half, so I end up with 1/2 B initial. If it's first order in B, if I cut the concentration of B in half, the rate should be cut in half. Well, if I cut A and B in half, then what does C decrease by? So this is C initial. C is being consumed at 3 times the rate. So I should be left with not 3/2 because then I'd be gaining. What would it be? 1/6. If this is 1/2, this would be 1/2. This would be 1/8. So I lost a half. I lost a half. Then I'm going to lose 3/2. I think I screwed this one up, maybe. I screwed it up because I can't lose half. Could I? I can't lose because I need because this would be my limiting reagent, so I screwed this one up. Sorry. Let me change this to 2. The reason I have to change it to 2 is because you're right. I would consume 3/2. But I only have. I'd consume more than I have. Right? And so if I made this 2, then this will be 1.
It's 1, right?
Just 1.
How do you have
Oh,
one?
no.
It's like the same as what we started with. Isn't that 1/4? Since you're consuming it twice the rate?
Yeah. If I consume it at twice the rate, then let's put some numbers here. If this were 1 mole, this were 1 mole, then this would be 2 moles. Problem is if I start off with 1 mole, 1 mole, 1 mole, right? And then this is the limiting range, and this goes down to 0. And so I screwed up again. I should have just used the numbers I used this morning. Let's go down 1/4. Sorry. So I lose 1/4, so I'm left with 3/4 A. And so let's say I consume 1/4, I consume 1/4. Then this should be 1/2. And so I'll be left with 1/2. C initial.
So that's assuming you have 1 molar each reactant.
If I had 1 molar each reactant, then this I'd get 0.75, 0.75, and 0.5. Does that make sense? All right, now I got some numbers here. And so what impact will that have on the rate? Okay, the rate is going to be a composite effect of all these, right? And so if I look at the rate will equal Ka. The concentration of A here is going to be 3/4 A initial. That's the new concentration of A, raised to the first power. The new concentration of B will be 3/4 B initial, raised to the first power. And then the concentration of C will be 1/2 concentration of C initial, raised to the first power. And so the composite effect is going to be here. We're going to factor out these coefficients here. So it's going to be 3/4 times 3/4 times 1/2. Ka initial to the first, B initial to the first, and C initial to the first. So even though I cut A, the overall rate is going to be impacted by not just A, it's A, B, and C, and it's going to be in this sense. 3 times 3 is 9, 4 times 4 is 16, times 2 is 32, so it's going to be 9/32, the original rate. The original rate is just K, A, initial to the first, B, initial to the first, and C, initial to the first. To see it being first order just in A, I'd have to make B and C huge, right? Make it pseudo M order. So this is what we're doing in today's lab. We have 2 reactants that are going to influence the rate of reaction. So today's lab, we're taking the reactant crystal violet plus, we'll just abbreviate CV plus, and hydroxide. This forms crystal violet hydroxide. Well, crystal violet turns out to be purple in color. And so visually, we could follow this reaction along because crystal violet starts off as purple, hydroxide is colorless, and crystal violet hydroxide is colorless. And so as the reaction proceeds, we lose the purple color, and it becomes colorless. And the color just fades. And so we could track the progress of reaction by just watching the crystal violet color disappear. And so what we're going to do is we're going to make this pseudo M order. And so in order to make it pseudo M order, because the rate should depend on both, the rate is going to equal K times the crystal violet plus concentration to the N power and hydroxide concentration to the N power. Now M and M, even though the coefficients here are 1 and 1, M and N aren't related to those coefficients. In general, this is what we see. You know, if I have a reaction AA plus BB plus C, etc., the rate law is not necessarily equal to K, A to the little a, B to the little b, C to the little c. Sometimes it's equal, sometimes it's not. It depends. And since that's the case, then all we can say that is true always is that the rate will equal K, and then we come up with some new variable. Rather than A, which is related to the coefficient here, we just call it M, B to the N. Where M and N might not be related to A and B here, the coefficients. So we need to figure out what M and N are. Let's start off with M. So if we make this pseudo M order, what do we need to do? Yeah, what we're going to do is we're going to just use a very high concentration of hydroxide, so high that during the course of the reaction, it barely changes. This way, when we're watching the crystal violet disappear, we're just seeing the effect of crystal violet alone. And so if it comes out linear, then it's 0 order, right? If it comes out exponential with a constant half-life, it's and then if the half-life is doubling, then it's second order. And so we can see that easily. And so this is the way we're going to start the experiment. How we're going to monitor the color, though, is we're going to monitor it quantitatively using a spectrophotometer or spectrometer. And so this is the spectrophotometer here. Maybe I've used this in Chem 1A. We're going to work in groups of 2 to 3. So go ahead and check out the equipment now, and we're going to work through it together. Okay.